You ever think about the foam in your car seat? The stuff that's got to be both comfortable and somehow last for years? Well, that doesn't happen by magic. And it's definitely not just mixing a few chemicals together. It's an intentionally engineered material. And in this explainer, we're going to pull back the curtain and show you exactly how it's designed.
Right, so how do you actually get that perfect balance, that blend of softness, support, and just plain durability? Well, it all comes down to a series of really strategic choices right from the very beginning, and it all starts with two fundamental building blocks.
First up, we've got the polyol. Now, I want you to think of the polyol as the architect of the foam. Seriously. It's what lays down the blueprint, creating the fundamental backbone that's going to determine everything. And I mean everything, from the foam's strength to how stable it is long-term. You get this part right, and you've got a rock-solid foundation to build on.
And this brings us to this idea of polyol architecture. It's really just the art of strategically picking and blending different polyols to control the foam's final properties, everything from its internal cell structure all the way down to its long-term durability. So our architect has two main tools in the toolbox. On one hand, you've got these things called sand solids. These act like microscopic rebar, reinforcing the cell walls to make them durable and to stop the foam from getting permanently squashed. Then, on the other hand, you have EO-tip trials. These are what provide the flexibility, the bounce, that comfortable, resilient feel we all want.
But here's the key. You have to use these tools correctly. A huge pro tip from formulators is to match the sand particle size, that's known as the D50 value, just a measure of the average particle size, to the foam's overall density. And this is especially important for those lighter, low-density foams. So why is that?
Well, the reason is all about proper integration. When you use fine solids in a low-density foam, you create these really strong, durable cell walls. But if the particles are too coarse, too large, they just don't blend in right. They actually become weak points in the structure, which leads to brittleness and defects. It's a perfect example of precision engineering at a totally microscopic level.
Okay, let's move on to our second key player. If the polyol is the architect, then the isocyanate is the activator. This is the component that kicks off the chemical reaction. By choosing the right one, you control the how and the when of foam formation, its speed, the way it flows into a mold, and even its final texture.
And this table really highlights the key strategic choices. For instance, if you need to slow down the reaction for a really complex mold, you'd use an MDI with a high 2,4 isomer content. If you're dealing with specific mixing equipment, you'd focus on the PMDI. And for the absolute most control over the reaction and emissions, you'd go with what's called the pre-polymer route.
So what exactly is this prep polymer route? It's actually a really clever two-step process. First, you pre-react the isocyanate with some of the polyol. This creates a more stable, less volatile intermediate compound. Then, you use this new intermediate in your final mix. The result? A much more controlled, predictable reaction. It's perfect for thick parts, or anytime emissions are a big concern.
But that level of control does come at a price. A key piece of advice here is to use the pre-polymer route only when you absolutely have to. It can get expensive, and it can limit your flexibility to make other adjustments later on. So it's a powerful tool, but you save it for when the reaction chemistry truly demands it.
Okay, so we've got our architect and our activator. Now let's talk about the master dial that fine-tunes the entire performance, the isocyanate index. This is basically just the ratio of isocyanate to polyol. But trust me, a tiny little change here has a massive impact on the final product.
Just look at this number, +5, a 5-point increase. It seems so insignificant, right? But in the world of foam chemistry, that is a huge shift. So what does turning the dial up by just 5 points actually do?
Well, it's a classic trade-off. Increasing the index makes the foam firmer and more resistant to creep over time, which is great for durability. The flip side, though, is that it also generates more heat during the reaction, and that increases the risk of scorching or discoloration deep inside the foam.
Okay, so what happens if we turn the dial the other way? Let's drop the index by just 5 points. Again, it's a small adjustment, but it comes with a completely different set of consequences.
Dropping the index gives you a softer feeling foam, and it can often improve that initial new foam smell. The downside? You run the risk of what's called set growth. That's where the foam doesn't fully recover its shape after being compressed, leading to permanent indentations. Not good.
So we've covered the architect, the activator, and the master dial. Let's wrap this all up and look at the key takeaways for designing the perfect foam. All right, here are your master keys. 1. Polyol architecture is your foundation, so match that sand particle size to your density. 2. Isocyanate selection controls the reaction timing. 3. The index is your fine-tuning dial. And finally, number 4, it's all about balancing the urea to urethane ratio. This is the core chemistry at play. Just think of urea groups providing hardness and structure, while the urethane groups provide elasticity and flexibility. Getting that balance right is what ultimately delivers the performance you're after.
From the architect to the activator to that master dial, you now have the strategic framework for how performance foams are truly engineered. It's this powerful combination of chemistry and physics. So the only question left is, now that you know the levers of foam design, what will you build?